Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, we're revisiting the Zenith ZT-1. This is going to be part 3 in the series where I'm trying to get the Zenith ZT-1 working again. If you haven't seen part 1 and 2, I recommend you watch those first because I'll be continuing where we left off in part 2 in this video. Now, as a quick recap, this is the Zenith ZT-1, which was a 1982 information terminal type device. It was for home and business users. It has a built-in 300 baud modem, and it allows you to easily and quickly dial up to information services like CompuServe without having to have a computer. The unit I have here was brand new in box, but really probably never worked properly because when I got it, it was already taken apart and someone had just placed it back in the box. The machine, when I first powered up, wasn't really showing any signs of life. There was some activity on the data bus, address bus, but really there was no video output whatsoever. But then we had some power supply issues where a tantalum shorted and it took out the external power supply. So in part 2, I got that power supply working again, and then I did some really deep troubleshooting by disassembling the ROMs using the help of AI and tried to get to the bottom of exactly what was wrong with the machine. And it turns out that everything pointed to the video chip being the failure point. So I ordered a new replacement video chip, put it on the board, and the thing actually came to life. It still has issues, but at least it was showing signs of life. It had video output. So at the end of the video, I create a list with some things we need to take a look at and try to address in part 3. And if I can get this thing fully working, I want to try it out by actually dialing into it and also dialing out as if we're dialing up to an information service. So without further ado, let's get right to it. Here's the ZT-1, pretty much as we left it. We have the replaced or bad video chip, and at the end of the first part, I had taken out the SRAM chip that stores the configuration values. That's this chip right here. But I came to the conclusion there's probably nothing wrong with the original chip that I took out, so I'll just be swapping those back out. This is a normal 2114 SRAM. Even though the chip on the motherboard had the marking D444C, my friend CJ did a little cross-referencing and found that some of the NEC 2114 chips had a label that was like 444 on them, so we pretty much assumed that this was just a normal 2114. Now, the eagle-eyed among you may notice that I have this sitting off the board, which I didn't have at the end of part 2. Well, in the interim, I did a couple things just to prepare for this video, and one of them was hooking this battery up to the motherboard. This is a regular 1.2 volt nickel metal hydride, just a AA type cell. But since I don't have a single battery holder, I just used an elastic band to hold these wires in place, and then I did solder it onto the 2 points on the motherboard where the original battery was connected. Well, not quite, because those things were corroded from the leakage, but this resistor and there's a tantalum over here, which are the 2 points that the positive and negative connect to from the original battery. When we take a look at the list of things that's left to fix on this thing, the major issue is the first column of all the text on screen seems to be missing. There was another issue where the video started glitching, but I theorized in part 2 that was a problem with the RetroTink, which is I was using to capture the video from this. The video that comes out of this seems to be somewhat non-standard, and normally when you plug in a CRT into a device like this, because it did come out in 1982 and was designed in 1980 or 81, well, CRTs are very tolerant of signals that are out of spec compared to what is NTSC standard. So I have a feeling the RetroTink was just sort of freaking out after a little while when why the video started glitching. So I grabbed an RGB to HDMI and one with the comparator board on it. That means it has analog inputs versus the 9-pin digital input of this one. And I went ahead and I created a profile for the ZT-1 specifically so that it could capture the entire image, because I was suspecting as well in part 2 that part of the image was being cut off and the RetroTink just was not able to digitize the bottom part of the video frame. It was just missing entirely. So with the RGB to HDMI, I can create a custom profile that's way more flexible than the RetroTink. So let's take a look at where we are now with this new capture device and the battery installed on this terminal. All right, let me power up the machine. Now, the fault of this experience where the first column of letters is missing, that is still absolutely there. So we can move the cursor over to that part of the screen, which is right there, but nothing we type in this first column will ever actually print anything on screen. But what I figured out at the end of part 2 is that if I type stuff in the very far right column, then it seems the very last letter starts to appear in that first column, but it flickers between 2 characters, and it seems to flicker between the very last character in the line and the first character. So right now you see a G mainly, but it looks like there's an F there as well. If I type a hash symbol, which is Shift 3, now you'll notice it's flickering between the hash symbol and the G, which is at the end of the line. This is identical to what was happening at the end of part 2, so nothing has changed when it comes to the remaining fault that this machine has. Now, if we hit the help key, that takes us into the menu. Notice there's a phone book entry. And I added that specifically because once I put the battery in, I wanted to just validate that the circuit that saves to the SRAM chip is actually working. And it totally is. This machine has been off for hours and that phone book entry is still there. Now we are still missing the entire first column on the left side. There should be a line that goes around the boxes and that is gone. Now we can hit F3 for setup. And off camera, I played around in here a little bit and I figured out a few interesting things. So any of the items that are listed here that are configurable that have an asterisk next to them, so that's A, D, and Q, those are all settings that don't get saved into the battery backed up SRAM. But all the other settings that are listed here do. So for instance, I have clock display, that is item B, turned off right now. And that was on when the machine just factory defaulted itself. So it showed the clock in the upper right corner of the screen. And that absolutely does save across power resets. Now, one of the issues I was having is if we change something, like let's change the value of B, let's make it back to on. So now the clock is in the upper right corner. Well, what was happening with the RetroTink, and when I was first testing this, I thought it had a fault because I hit F4 to save, and it basically seemed like the computer was frozen because I could no longer exit out of anything. I couldn't push the quit button to leave. And that's because the very bottom line of text there where it says hold save button and then hit enter, well, that was missing on the RetroTink. I couldn't see that, and no amount of adjusting in the settings of the RetroTink would allow me to see that. But as you can see here, we have a pixel perfect capture of the display output with the RGB to HDMI. And you can see I even created a profile for the ZT-1. It says profile down at the bottom. And these are the settings I figured out for this device that seem to work perfectly, at least with mine. And just for completeness, I'll share this profile for the RGB to HDMI with Ian, who maintains the project. So if anyone else has a ZT-1 and you have an analog comparator board for your RGB to HDMI, you could use your ZT-1 or ZT-10 or ZT-11 with the RGB to HDMI if you want to get pixel perfect display output. And that'd be useful because I'm quite sure, and I haven't tested this, but I'm pretty sure if you plug this into a normal CRT or most CRT monitors, even computer monitors, composite computer monitors, I have a feeling most of the edges are going to be cut off because a lot of 8-bit computers like the Apple II had a big black border around the edge as it was designed to be used with something like a television set. This seems to be designed with computer monitors in mind, like the Zenith ZT-1, I think it was called, which has geometry set up on it where you pretty much see the entire NTSC image on the CRT, and the border you see around the edge is beyond the edges of the NTSC frame. So when they designed the video output on this, they pretty much decided, yeah, let's just use the entire image to get, I don't know, the highest resolution text and the most number of lines possible. Anyhow, when I hold down the save key, which is the button on the back, and I hit enter, well, that absolutely does save the settings. And now that the clock is on, if we power the machine off and we power it back on, now the clock is displayed in the upper corner. Now, as I pointed out, A has an asterisk next to it. That's the time set. That means the time absolutely gets lost when you power cycle the machine, which is pretty much what I thought. There's no crystal oscillator on this machine. So even though the battery maintains the SRAM, there's no separate clock circuitry on here, like a Dallas clock or anything else that could keep time while the machine is off. The time that this thing keeps while it's running, I'm quite sure is one of the timers that's inside the microcontroller, and I'm almost positive, but I don't have the schematics yet, that the 60 hertz line frequency comes in from the AC transformer and is turned into a digital signal that goes into one of the GPIO lines on the microcontroller. So if we poke around on all the inputs, I bet we're going to find one of them with like a 60 hertz or 120 hertz square wave on it. That allows this thing, while it's running, to keep pretty much perfect time because the utilities, at least they did back in the 80s, make sure any clocks driven by the line frequency keep perfect time. And they do that by speeding up and slowing down the waveform just so slightly so that it has a perfect average of 60 cycles per second. So we know that the battery backed up SRAM circuit works perfectly on here. Now remember when I was doing the initial troubleshooting, I was curious about why we were getting clicks out of the relays on the modem. These are these green blocks, and now we don't. Well, I still don't know why that was happening, but I can confirm at this point the relays on here never click when you power the machine on and off, but they do click if you try to dial. And I haven't actually tested this by plugging in a phone line, but if we hit A to dial that phone book entry, so as you can hear there, it is clicking, and that means that this thing is using pulse dialing to dial the phone numbers, which is pretty much what I expected. The manual, which we read through in part 1, talked no mention about touch tone dialing whatsoever, even though in one of the photographs in the manual, it showed someone with a touch tone telephone. So touch tone existed at that point, but in 1982, when this thing was actually released to the public, you pretty much need to have modems that supported pulse dialing and touch tone dialing because a lot of people didn't have touch tone dialing in North America. Initially, that was an optional pay service that you had to pay your phone company to have. It was like a couple extra dollars a month on your phone bill just to dial with touch tone, which seems kind of hilarious when you think about it. But I do remember the days, and I had friends who didn't have touch tone dialing, and they used to BBS a lot, and it took them much longer to keep redialing the BBSs. Because if you remember your BBS days, you'd call your favorite BBS. It was busy because they only had one line. So what you would do is you'd have your computer constantly redial the number so that you could try to get on as soon as that other person hung up and you wanted to get on before someone else did. Well, with touch tone dialing, you could speed up the touch tone dialing to be pretty quick, but with pulse dialing, you know, tick, tick, tick is slow. So it just took a lot longer. So it was a nice convenience to have touch tone dialing. So looking back at our fault list, the glitching video, obviously, that was a RetroTink artifact. So that is a solved issue. So really all we're left with that's wrong with this machine at this point is this one here, where the first column is showing the last. Well, it's kind of showing the last, also showing the first, but it's clearly not working correctly. Well, at the end of the last video, I gave some thought to what might be causing that particular fault. And you might just jump to the conclusion right away that it's got to be the SRAM chip that is the video memory buffer. Like it somehow must be bad, or there's some kind of addressing error in there. As far as I'm aware, there's no RAM tests or anything that happen on this thing. So yeah, it could be bad, and that could be causing this fault. But I don't really think so. We have to remember that the video memory on this computer is just a 2K SRAM. It's not designed inherently to work as an 80 by 24 or 80 by 25 video buffer. So what are the chances that the first column of every single line in this arbitrary screen buffer is somehow messed up or addressed wrong internally to the chip? That doesn't really make sense to me, at least. I feel that there's got to be some other fault on this machine, and that is not specifically the SRAM. Now, it goes without saying that everything on this motherboard is socketed. So I have another 6116 SRAM. We could just swap this in just to see what happens, and I suppose that's worth doing. But you know me, I always like to try to understand what's causing the fault first. It's quite within the realm of possibility that every chip on this motherboard could be soldered, and we'd have to remove the SRAM chip just to do the test of trying a different one. Not to mention if you didn't have a spare like I do, you'd have to buy one as well. And it goes without saying that while I can remove a chip using my Hakko 301 desoldering iron here, it's not always that easy for everyone, and taking a chip off the board can easily damage the board, and you can introduce new faults that make the problem worse, and it could be subtle faults that are hard to find. But with all that said, I have the extra chip here. It's in a socket. It doesn't hurt to swap it out, so I'm just going to turn the power off, and let's give that a try. Now, one thing to consider about these SRAM chips is they work a lot more like an EEPROM. They don't have row and column stuff happening like DRAM does, where you need multiplexers and a bunch of extra support logic to access all the memory locations. They simply have address lines going into them, and then they have 8 data lines. So to access any particular location in memory, you just set up the address lines appropriately, and then you assert the chip select line, and that will just output the contents of whatever that address is to the data bus. Or if the write signal going into the chip is asserted, and then you assert the chip enable line, then whatever's on the bus, like from the CPU, will be written into the chip. And that might be for clearing the contents or putting text on screen or whatever. One thing we can test is, let's see what happens if we leave this off and turn on the computer. What will that do exactly? One thing that's cool about the RGB HDMI is it doesn't need to synchronize, so we'll instantly see whatever's going on with the computer as soon as we turn it on. Will this computer initialize properly? We'll kind of know that because when you turn this on, you get a beep out of the speaker here. Here we go, 3, 2, 1. Okay. It's very unhappy, obviously. Interesting that the beep did stop, but I assume that's the key click we're hearing. But the CPU is obviously held a lot longer than it normally is. So a normally short key click is now a beep, and that initial power up beep was really long as well. All right, so that's kind of curious. The chip on the bottom is the one I just took out, and the one on the top is the one I'm going to put in. They're both Hitachi parts. This does have a tick mark on it, so I guess I've tested it at some point. And this one's from 1985, but we don't know where this one's from because it has a date code that I can't decipher. I am fully expecting this to have no effect whatsoever. I think the machine will be broken in exactly the same way as it was before. Let's turn this on, 3, 2, 1. Okay, normal beep and normal key clicks. And yep, just like I thought, the fault has not changed at all. I feel in a way whatever's happening is whatever loads the data from the video RAM to be displayed is not selecting the video RAM quickly enough, or something like that. Like it's maybe picking up what was on the bus before. Like if you leave an open bus when you make a read request, you pretty much get what was on the bus before. And well, I guess that's not that either, because we would be seeing instructions because the CPU is running instructions. I'm not 100% sure. We're gonna have to do a little bit more thought about what might be going on. I think the first thing I want to do though is restore this back to its original VRAM SRAM chip and its original SRAM chip for the NVRAM or the settings storage, because why not have it all original? I mean, we know the video chip so far, the only thing that needed to be replaced to get this thing working. But I suppose I should disconnect the battery before we change out the SRAM chip. And since I did check the 1.2 volts, it looks like it goes through a diode or something. There's a bit of a diode drop, and it makes its way over to this chip at about 1 volt. Which makes me think that's possibly why they use this 444C product versus this normal NEC 2114. Perhaps this 444C runs at a lower voltage and stores the content for longer. It's not very clear from the data sheets like what voltages this will work down to, at least for just keeping its contents stored properly. All right, we're back to our original chips. Let's turn this on. Still got a normal beep. No changes over here. I know when I hit help, I think basically it's going to set the NVRAM up to factory default, so it makes me push the button and push enter. And we lost our phone book entry, as would be expected. To change the directory entry, you have to hit F2, you have to hit F1, you have to push the letter you want to add, type in the name, and then type in a phone number. And then it's asking you what type of system you're calling. Is it source, direct, which I guess is some online service, telenet, timenet, data, or voice? Well, I just picked data because we're going to be testing later with just calling a modem. My assumption is when you use one of those other ones, it actually allows you to type your username and password in, and that will save as well. Actually, let's test that. So to save this, you then have to push the button on the back, which I'm assuming is like connecting the right line to the NVRAM. We hit enter, and it does save it. And the D is for data. So we'll do the process again. We'll make a new entry, B. We'll just call it test, put a different phone number in, and let's try source direct, log on. I'm assuming it says log on, but pretty much sure it is that. Adrian.black. Okay. Yes. Press the save button. Push enter. Perhaps the usernames on those services were a lot more complicated than just Adrian. It probably was a bunch of numbers or something like that. It probably just helped you to get into those more quickly because all you had to do is remember your password at that point. I know there's some other options in here that'd be fun to play around with, but first we need to test to make sure that the battery's working. So power is off right now. Turn it back on. Push help. There are 2 directory entries. Okay, so this SRAM chip is working. So other than our fault with that first column, it seems that operationally this thing is working. Now I haven't actually tested the modem connecting to something else, so maybe the modem's broken, don't quite know for sure. But the keyboard is working, the CPU seems to be working, ROMs are working, character ROM is working. Well, video chip is working, I suppose. And so is the 2K of SRAM, and then we have 1K of SRAM right here on the motherboard, which I assume is like a main memory or a scratch memory or something. That seems to be working as well. So let's give some deeper thought as to what might be causing this video issue. In part 2, I just quickly alluded to the fact that like the CRTC, that's the chip I replaced, it just displays the contents of memory on screen, and you know that seems to be working, right? We have clear text and it's not glitchy or anything like that. But what mechanism does it use to actually load the contents of that SRAM chip, the 2K SRAM, to then display it? Because it has to get from that chip somehow to the character generator, which is what then gets turned into pixel data via a shift register and displayed on screen. How does that part of the process happen? I kind of glazed over in part 2, and the reason why is I never really looked into that. I never really thought to try to understand that. The 6845 on the CGA card and the MDA card, for instance, or on the Commodore PET that uses a 6545, I think those work with a very similar mechanism to the Intel 8275 that this thing is using. And now we have a Siemens version of that chip in here. But to be honest, I never really looked into exactly how those chips display the contents of the screen buffer to screen either. I know they help in that process, and you don't have to use one. The Apple II doesn't have any kind of CRT controller. It does everything through TTL logic. Even the original Commodore PET does it all through TTL logic. It's just the CRTC, I think, simplifies a bunch of that stuff. But like I said, how does it actually work? And then specifically with this 8275, well, I replaced it with a Siemens part, which should be compatible, but is it really? So let's take a look at the 8275 data sheets, and we'll start with the Siemens one because that's the one that's in this machine right now. And if for some reason it's not really compatible with the Intel one, well, then that could just be our problem right here, right? So let's start with that one. So the Siemens SAB 8275 programmable CRT controller. Programmable screen and character format, 6 independent visual field attributes, 11 visual character attributes, cursor controls, light pen detector and registers, dual row buffers, programmable DMA burst mode, single 5-volt supply, high performance NIMOS technology, fully compatible with the industry standard 8275. That bullet point is what I saw when I ordered this chip, when I figured out that this was cheaper than the Intel one, because when it says stuff like that, you'd think it's just fully drop-in compatible. I hope it still is. Starting at the bottom, address line 0, we know that has to do with the registers. There are 2 registers in the CPU, and you need to toggle that line depending on what you're doing with the registers. We looked at that when we disassembled the ROMs and we used the logic analyzer in part 2. Chip select is self-explanatory. That's anytime the chip is being accessed, it needs to have that line asserted so it knows to listen on the bus. Then it has character codes, CC0 through CC6. I have a feeling these are address lines that go to the character generator EEPROM that essentially select one of 128 characters, because it would be 256 if it had 8 bits, but it only has 0 through 6, so it only supports, it looks like, 128 characters. And I think this is what's selecting the character, which character to draw out based on the content of the video memory. And in conjunction with the character code, you need to have a line code, because each character is made up of lines of pixels, rows of pixels. And because we have 4 lines, it appears that this supports characters that are up to 16 lines tall. Now, when it comes to the width of a character, remember we're using a character ROM that's an 8-bit EEPROM, so that means it can support outputting up to 8 pixels. And the shift register converts that row of 8 pixels, that parallel data, into serial data. Anyways, back to what we see here. So there's an interrupt request, so an IRQ line. I guess maybe that has to do with clocks or who knows what. We have highlight, which I think is an output for like one of the attributes. So if you want to have probably brighter text like monochrome video does, MDA has a dimmer and a brighter, an extra bit there. Oh, and then there's line attribute codes. You can run all that stuff into your character generator if you want to have more characters. And for instance, if you turned on reverse text, well, inside your character ROM, you would just have a set of all your characters stored with, inverted. And you could have special characters by using the highlight bit, stuff like that. General purpose attribute codes, GPA 0 and 1, same thing. Those could be used for graphical characters, stuff like that. Video suppression probably goes to the shift register and it shuts off the video. Then we have data bit 0 through 7, which is a bidirectional 3-state data bus, right? So this is how this chip is connected to the data bus. We know for sure the CPU is talking to the chip. It's reading and writing registers from it, and that is going to be using those data bits. But I'm now thinking, because look up here, there's DMA stuff. I wouldn't be surprised if this chip is supposed to work in conjunction with a DMA controller to load the contents of SRAM into a buffer that's in this chip. And where did we see that? We saw it here, dual row buffers. I'm thinking there's actually a buffer inside of this chip where the contents of the video RAM gets copied into this chip, and then this chip is what then reads its buffer and instructs the character generator to generate the appropriate characters. It also has a read and write line that's self-explanatory, and sorry about that, I didn't have my cursor highlighter on. Then we have vertical retrace, horizontal retrace, so it's just self-explanatory. Those are going to be those 2 retrace output, and then we have those DMA lines. Now, when we look at these signals, DRQ is the DMA request, output signal to the SAB, or Intel for that matter, 8237 DMA controller, requesting a DMA cycle. Then there's a DAC line, which is going to be the DMA acknowledge line, and it looks like that's an input, and it says input signal from the DMA controller acknowledging that the requested DMA cycle has been granted. The character codes outputs, that's 0 through 6, output from the row buffers. Yep, there's talking about the row buffers again, used for character selection in the character generator. So that's definitely going to be going to the address lines of the character generator EEPROM. So the block diagram, yeah, so let's start at the bottom. We can ignore the light pen stuff. Raster timing, video control, that's all working fine. No problems there. Row counter, line counter. There's some FIFOs, but look at this. So the data bus connections that go to the system, they go into the chip itself, and then they are connected to a buffer input controller and an output controller. The input controller makes its way to some FIFOs, and it also makes its way to 2 80 by 8 character row buffers. And we look at what the row buffers are. The row buffers are 2 80 character buffers. They are filled from the microcomputer system memory while the character codes are displayed. While one row buffer is displaying a row of characters, so it's like actively drawing out the characters, using the character ROM, the other is being filled with the next row of characters. So it's like the chip is actually kind of multitasking internally. And while one is literally instructing the character generator to generate that row of characters, all 80 characters across, the next buffer is being filled with the following line of text out of the system memory. The buffer I/O controllers decode the characters being placed in the row buffers. If the character is a character attribute, field attribute, or special code, these controllers control the appropriate action. Examples: an end screen stop DMA special code will cause the buffer input controller to stop further DMA requests. All right, so this is very interesting. This is pretty much telling us, and let's talk about the DMA stuff here. A high on this output informs the DMA controller that the video chip requires a DMA transfer, and a low on this input informs the video chip that a DMA cycle is in progress. Now, this is pretty much telling us that it looks like what happens is the contents of the SRAM, the video SRAM, gets loaded line by line into the video chip and then displayed on screen. Now, the funny thing is, when we take a look at the block diagram for an entire system that's using this video chip, so there's the 8275, well, the one thing that's missing on this design is an 8237 DMA controller. And that is used on the IBM PC, for instance, to control DMA. And there's like 3 DMA channels, or was it 4 DMA channels, 0 through 3. And ultimately, if you're using the CRT controller on that design, you would hook up the DMA request line to one of those DMA channels, and then you would program your DMA controller that when that line was asserted, the DMA controller would take control of the system bus, right, by taking it away from the CPU, and then it would go and read out some of the contents of the SRAM, the video SRAM. I guess it would put it on the data bus for the CRT controller to like pick up off the data bus and load into the row buffer. So that kind of tells us there's TTL logic on here that's, well, emulating the functionality of this, and maybe some of that is what the problem is, and it's not getting the data on the bus quickly enough for at least that first character to show up in the row buffer. Although if you think about it, the last character on the line seems to get loaded into that first character spot, but it's flickering very, very quickly at like 60 times a second, which means like every time it refreshes the output, it's sometimes loading the character and sometimes it's not. And occasionally, remember we looked at some of the setup screens, you see like other weird random characters and stuff there, which doesn't quite entirely make sense. But it really feels like there's some type of a timing issue here. And that now kind of makes me think that the emulation of the DMA controller that they're doing on this system is so close in the timing tolerances that maybe this chip versus the Intel one was enough to cause this problem to happen, because this chip is maybe faster or somehow not 100% electrically compatible. And this thing is so on the edge of working or not working that it was my decision at buying the Siemens chip, which is probably not a bad chip, but just not exactly the same, that's causing this particular issue. Let's read up on this DMA timing so we can just try to understand this a little bit, or so I can try to understand this a little bit. The 8275 can be programmed to request burst DMA transfers of 1 to 8 characters. The interval between bursts is also programmable from 0 to 55 character clock periods. This allows the user to tailor his DMA overhead to fit the system needs. The first DMA request of the frame occurs 1 row time. What's a row time? Before the end of the vertical retrace. The DMA requests continue as programmed until the row buffer is filled. If a row buffer is filled in the middle of a burst, the SAB 8275 terminates the burst and resets the burst counter. No more DMA requests will occur until the beginning of the next row. So that's the next row of 80 columns. At the time, DMA requests are activated as programmed until the other buffer is full. So remember, it fills up one line, stops, then it fills up the next one, stops. A DMA request for the row will start at the first character clock. If the burst mode is used, the first DMA request may occur a number of character clocks later. This number is equal to the programmed burst space. If for any reason there is a DMA underrun, a flag in the status word will be set. All right, so what this timing diagram is trying to tell us, so we have the last row of characters being printed, then we have the vertical retrace being toggled, and then the first row is going to be filled. Next row buffer is filled, and I guess it can take multiple requests because it looks like they can have up to 1 to 8 characters per request. So say it's set to 1 character request, you're going to need 80 of these requests to transfer 80 characters into the chip. And if you do 80 requests, that holds the bus up and takes away from the CPU, versus if you do 8 characters at a time, it does it more quickly. Now it's funny, you can't just do 80 characters at a time, but whatever, I guess that's the design of this thing, which I think the date on this chip is 1976. So kind of an old design. And it's talking about interrupt timing, which I don't think is used necessarily in this case, although maybe it is. I forgot what the values were we were looking at when it was initializing the video chip. The chip can be programmed to generate interrupt requests at the end of each frame. This can be used to reinitialize the DMA controller. If the 8275 interrupt enable flag is set, interrupt requests will occur at the beginning of the last display row. If we were only having a problem with the very first character at the very top edge of the screen, that might have something to do with like the vertical retrace, which is the first top left character, but we're not. It's the first row, right, on the left side. It's every line that's having a problem. So I really don't think it's anything to do with this. The 8275 provides a window into the microcomputer system memory. Display characters are retrieved from memory and displayed on a row-by-row basis. The 8275 has 2 row buffers. 1 row buffer is used for display, and the other is being filled with the next row. It's kind of what we talked about already. The number of display characters per row and the number of character rows per frame are software programmable. I know for a fact because we looked at those tables in here that 80 characters across, and that's to do with the buffer on here can only hold 80 characters across. Before the start of a frame, the 8275 requests DMA and one row buffer is filled with characters. When the first horizontal sweep is started, character codes are output to the character generator from the row buffer that was just filled. Simultaneously, DMA begins filling the other row buffer with the next row of characters. After all the lines of character rows are scanned, the roles of the two buffers are reversed and the same procedures follow for the next row. This is repeated until the end of the character rows are displayed, so the full screen is displayed. Now we have a whole section on the attributes. I don't think that necessarily matters. Light pen doesn't matter. And then we have the programming stuff. So this is what we looked at in part 2. Now, of course, this is a different data sheet. I'm sure everything here is identical, but let's look and see if this is a little easier to understand. This all looks very, very similar. So characters per row, vertical rows per frame, underline placement. I think this is not really relevant to this problem. Horizontal retrace count, line modes, field attributes. This is all stuff that's not that important. Okay, start display command. I have to go reference my other video to know what this was being set to, but these are the DMA setting. Number of DMA cycles per burst. My assumption is this is the 1 character all the way to 8 characters. And then number of character clocks between DMA requests. This is like a resting period that you can have between these requests. I went and took a look at the footage in part 2, and the very last thing that was sent was the command 23. And we take a look at the datasheet. We know that the start display command, the most significant bit is 001, 001, so 23 is absolutely the start display command. And the next 3 bits, SSS, happens to be 000, and that coincides with 0 character clocks between DMA requests. And the final 2 bits are BB, which equals 11. And if we look at 11, that is 8 characters per DMA burst. Then we have stop display, we don't worry about that, light pen, whatever, cursor position, interrupt control, and we have preset counter. I don't think that's really relevant. Then we have a status flag, which you have to read out of the chip if you want to know what's going on. And there is some stuff here in proper command, video enable, DMA underrun. That's that flag that can set. This flag is set whenever a data transfer underrun occurs during DMA transfers. Upon detection of a data underrun, the DMA operation is stopped and the screen is blanked until the vertical retrace interval. The flag is reset after a status read. So I guess that would just turn the whole screen off for 1 cycle, so like 1/60th of a second. So here's our timing for the DMA transfer. Now, it doesn't really explain what the burst transfers, like the multi-burst transfers would look like. So DMA request goes high, and that line is active high. So when it goes high, that means it's being turned on. That's supposed to go to a DMA controller, which then says, okay, fine, here's your DMA acknowledgement, and that's active low, because there's a line over it. So that goes low. And then a moment later, the chip is expecting to get a write signal, which is the data value that's being set up on the data bus for the character, so that this chip, the video chip, can suck that character in. And then the write line goes high, and then according to this, the DMA request line, which dropped off once it got the acknowledgement, goes high again, which is starting the next cycle, and this thing just sort of repeats over and over again. Now, like I said, my assumption is if you're writing 8 characters all at once instead of just 1, that this write line gets toggled 8 times, and each time this chip will pick up the character off the data bus and load it into its internal row buffer. This doesn't talk anything about the chip select line or any other line, so I'm assuming all those other lines are not relevant for DMA action, versus down here we have write timing, but I think this has to do with the registers, where chip select and the address line 0 is important. And it's funny because on the DMA timing stuff, it doesn't even talk about the data bus 0 to 7 validity, even though clearly it should be on here, because once the write is set up, the data bus needs to be set up as well at that point, and then that's where it's going to be picking up the data off the data bus. So I don't really know why it doesn't show that, but that's this particular data sheet at least. And then that's pretty much it for this data sheet. At the bottom here, it says the 8275p is a 2 megahertz version, and that's what we have on here. And there's also a 3 megahertz version, but I don't think that matters. I know the clock that's going into this, it was something like 1.4 megahertz or 1.6 megahertz, so it's within the 2 megahertz. Now I also have the Intel data sheet. We can take a look at this to see if there's like anything different about this when it comes to, I don't know, the DMA timing or anything. Maybe it has a bit better pictures about how that works. Looks like everything is the same, at least from the pins. So DRQ, DMA request, a high on this output informs the DMA controller that the 8075 requires a DMA transfers or desires a DMA transfer. And then the acknowledge informs that the DMA cycle is in progress. This block diagram looks identical to the one from the other data sheet. Everything here looks exactly the same. Oh, this one looks identical as well. It just doesn't put a part number on the dot timing interface, unlike the Siemens datasheet. The section on DMA timing, exactly the same between the two datasheets. When it comes to the register with the DMA transfer, exactly the same, 1 to 8 and 0 to 55. And unfortunately for DMA timing, it's like they copied the diagram directly out of the Intel datasheet into the Siemens one. It looks exactly the same. I have a bit of a better understanding now of how this CRT controller works. Definitely we have DMA transfers of some kind, and that's obviously supported either via the microcontroller itself or some additional TTL logic that copies character content out of the video display buffer and loads those onto the bus during these DMA transfers, and that loads them into the CRTC. And from a timing perspective, we're just off ever so slightly. And the reason why I say we're not grossly off, because if the transfers were way too slow, then the whole line might be shifted and we'd lose stuff off the end. But we're not. Everything is in the correct spot. It's just the very first row is not getting loaded correctly into the video chip, which I assume is because it's just being set up ever so slightly late. And there must be a difference when it comes to the timing on that very first column inside the video chip, that it expects it to be set up ever so slightly faster or more quickly than it's getting done here. Now, because we know that there's no DMA controller on here, and I'm pretty sure that this Intel microcontroller, the 8031, does not have DMA built in, this is being emulated in software, and I assume with some extra TTL logic. And one thing I can probably do is try to look at those two DMA lines that come out of this chip and see where they go on the board exactly. And do they make their way to the MCU, or do they just end up in TTL logic? Is there TTL logic that's somehow refreshing through this and doing it? But I don't think so. I think this is something that the microcontroller is going to do, because this is somewhat complex, and normally you would use that Intel DMA controller to do that stuff. So if you remember from the beginning of part 2, I found this one picture from the service manual for this device that actually shows the layout of all the pins, which is very helpful because this is quite a dense board, and figuring out like where a trace goes is not easy. So it's not super clear because it's just a photograph of a page, but it's certainly better than nothing at like finding where these traces are going. So I'm going to spend a moment to try to figure out where the DMA lines are going on here, and then we'll go from there. All right, I loaded it into GIMP so I could highlight the traces and zoom in on them, and then I had to tone some stuff out because some of this stuff is really, really hard to see. But I've been able to make some progress on exactly what's happening. So pin 5, which is the yellow trace, this is the DMA request line. And pin 6, which is the green trace, is the DMA acknowledged line. So let's start with the acknowledged line, because we know that the CRTC needs that line asserted, goes low, that is, when a DMA transfer is starting. Well, if we follow the green trace, we go over here, go down there, it makes its way over to this chip here, I think 115, which looks to be a 74LS32. Now I need to analyze the gates on there and figure out where that goes beyond there, because obviously I haven't done that yet. So that's the acknowledge line. Now the request line, which is the one that's saying, hey, I need a DMA transfer, I'm ready to fill my buffer, that's the yellow trace. Well, that makes its way over here to this IC, U121. Well, this happens to be a D-type flip-flop, and these types of flip-flops have 2 units in them. One unit's on the left side, one on the right. Well, it goes into the data input line on the D-type flip-flop, and out of that has 2 outputs. One is inverted from the other, and those 2 traces, which is this blue and purple trace, they make their way right to the microcontroller. So it's pin 13 and pin 12. And on the pinout for the 8031, that's P3.2 and 3.3, and that's interrupt 0 and interrupt 1. So these, I think, are programmable I/O lines, but they're traditionally used in one mode as the stuff that you see on the left here. So RX, TX, which we pretty much know we're using for the modem, right? Receive and transmit serial. But interrupt 0 and 1. So there's something programmed in the 8031, some code that's programmed in here, that when those lines get toggled or asserted, that executes that special code I was mentioning, which then will go and tell the video RAM chip to do a read, which then sets up the contents of that location on the bus, which then the CRTC picks up and sticks into its video buffer. And it probably does 1 character at a time. Now, I don't really know why they're using both interrupt lines, because the 2 Q outputs on the flip-flop, one is just inverted from the other. They're the same exact thing that's coming out of the flip-flop, but who knows what they're doing with the code. Now, the thing is, the flip-flop, well, if this is being slow, I mean, it's looks like it's an LS part. It's nothing particularly slow, but if we sped this up, by installing a faster part in there. I don't know if I have a faster part, but I did have a faster part. Potentially these interrupt lines would get triggered sooner, and then potentially the read that happens out of the video RAM chip, which is this one right here, that read will happen faster. It'll set up quicker on the data bus, and it might just be that nanosecond faster that is needed to get that first character into the buffer. Another thing we could try to do here is set up the logic analyzer again, take a look at the data bus like we did before, but also take a look at these DMA transfer lines, the two transfer lines, along with the chip select line on this ROM chip, and then maybe the write line that goes into the CRTC. That's each DMA transfer, remember, is using that write line to say, hey, pick up that data off the bus. I need to give a think about what the next thing I want to do is, and I think it's going to be the logic analyzer. That's going to be a theme for this video series for this thing, is using the logic analyzer, which I don't normally do. But I think using the logic analyzer might be fun to do just to try to see this DMA stuff in action, actually happening. Maybe we can see a problem. And then if I try to change out the chips for faster versions, then perhaps we can actually see the timing improve. I'm all set up, ready to capture. I have the 8275 connected up, and I did connect up to the flip-flop, so we're picking up the two interrupt lines that go to the CPU. These are the exact pins we're capturing, so D0 through D7, that's the data lines, and that's coming straight off the actual 8275. The DMA request line, the DMA acknowledge line, the write line, the two interrupt lines that are going to the CPU, that's off that flip-flop I just mentioned, and then we have the vertical retrace, and that's so we can see the start of the frame, so we can line the DMA transfers, so we can see that top line, which should say, what, press help for menu or whatever it says when you power on the machine. I also have the parallel decoder set up. That's data lines 0 through 7, and it's triggering off the write line. Because remember, based on the datasheet, anytime there's a DMA transfer into the CRTC, the write line should go low and then high. And even though the timing diagram for the DMA transfers doesn't really talk about the fact that it's going to be picking up the contents of the data bus and loading that into the row buffer, that's almost certainly going to be happening when the write line goes high. So this is where the data is going to be captured off the bus. It doesn't show that anywhere here, but we can take a look at write timing, which is going to be the same. And this has to do with writing to the registers, but you can see here, as the write line goes high, that is where the data bus needs to be valid. 0 through 7 must be valid in that exact moment as this is transitioning to high, which is very standard stuff when it comes to the way TTL logic circuits are designed. And we can see that the problem is still happening. I'm going to hit help just to bring up the menu. And incidentally, it's the next day, and you'll notice that the NVRAM with the battery there was maintained, still has those two phone book entries. And before I hit the start button to actually capture data, there's one caveat with my logic analyzer. This is the very low-end model, it has a very small internal buffer. Well, I found out if I set this to stream mode, which means it's actually streaming over USB, the maximum transfer rate we can do when we're using all 16 channels, and we are using 14 channels, is actually 20 megahertz. And that turns out that that's not fast enough to capture the transitions correctly. We need to run in buffered mode because we have to run at a higher speed. Now we're not capturing those two channels, but that doesn't really change the fact that 100 megahertz is our maximum speed. And I found with a little bit of testing, which I have done off camera, that 50 megahertz is pretty much the minimum speed that I can capture at to get all the timing correct to make sure we capture the data off the bus correctly. And that leaves us with a total buffer of 368 microseconds, which is not very much. You have to think about the fact that an entire frame of video is 16 milliseconds, so significantly longer than that. And in case you're wondering, there is an RLE compression option, but that does not seem to work properly on my basic model here. If I turn that on, the captures don't work at all. So let's hit capture, and when we zoom out, the maximum we are going to capture is one set of DMA transfer. That's it. What we're looking at right there is one set of DMA transfers for one row of text. Now remember, we didn't know if it was transferring 1 byte at a time or 8 bytes at a time, because remember that was the maximum DMA transfer window size. Well, we can actually take a closer look and see exactly what's happening. So we're capturing the line on screen that says M, the phone book entry that says M. Well, let's take a look at the signals that we're looking at. So I'm triggering off the DMA request line when it goes high, and that's happening right there. And remember, the way the timing is supposed to work is that once this is asserted by the actual CRTC, then the DMA controller, which happens to be the CPU in this case, is going to respond with the DAC signal, and that's going to go low. Well, remember, we have that flip-flop that the DMA request signal goes into, and that generates the int1 and int0 signals that go to the CPU. Well, zooming in, we can see that those signals get asserted pretty quickly. Oddly enough, they don't get asserted at exactly the same time, so there must be a slight amount of propagation delay inside the flip-flop, but either way, those get asserted. Well, a whole bunch of time passes before DAC gets asserted. And I guess that's the CPU essentially being interrupted by these interrupt signals, and then it's executing some code, getting itself ready to start to transfer this data into the CRTC. So I'm scrolling over here, and right there is where the DAC signal gets asserted, and that's coming from, well, we don't exactly know where it's coming from. I'm assuming it's coming from the CPU. And it goes through some logic. There's probably, I think it went to an inverter or an AND gate or something like that. So I'll put a mark as soon as the interrupt gets triggered on the CPU, and that's this blue mark, so 3.12 microseconds after the trigger of the capture started. And then the actual DAC signal gets asserted at 53.72 microseconds. So it takes about 50 microseconds for that signal to get asserted, and that's where the DMA transfer itself begins. So DAC gets asserted, and that means that the CRTC is going to start watching for the write signal, and then it's going to start picking up the data bits off the bus. Well, the very first one it picks up happens right there. That's where the write signal goes high, and it captures whatever is on the bus at that exact moment. And I think this is actually coming from the 6116 2K SRAM itself. That's probably what's setting up the data bus. And you can see the parallel decoder, that first character looks like it's a 00. And then what we need to start doing is looking at every transition where the write line goes high, and that is telling us that a character is being loaded into the row buffer. And it looks like the first character is 00, then the letter I, so I have ASCII decoding turned on, and then hex 20, which is a space, so we have a bunch of spaces. And we can see at this point, the DRQ or the DMA request line gets triggered again. I think this is pretty much telling us that it's transferring 8 bytes at a time into the buffer. Because if I just remove that first transfer when the DAC gets asserted, so we have 1, 2, 3, 4, 5, 6, 7, 8 transfers, which was the maximum allowed, and then that DRQ gets asserted again, and then there are 8 more transfers, and then it gets asserted, 8 more transfers again, and it gets asserted, and so on and so forth. And there's a space, then we have 00, which we can assume means, I guess, the graphic character, the vertical bar that's next to the letter V, that's a phone book entry. And for instance, you see a little spike right there, but that's okay, because if we zoom in a little bit, that's not a problem. It's right there where the write line goes from low to high that the data bus is captured, and that's what sets up this space character. What happens after that point when write is up at 5 volts doesn't matter. And that's because I think it's like the SRAM chip is setting up the next value on the data bus. And all that really matters is the next time the write line goes high again, which happens to be right there. Well, since the DMA transfer is handling 8 characters at a time, there should be 10 DMA requests, right, for the 80 characters across. Well, if we take a look at the transitions here, that matches up. The first DMA request happens over off the left side, it's off the edge of the screen. That's the first transfer. And then we have 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the 10th transfer. And on that last transfer, there are the 8 additional writes that are the last characters in the buffer, which we know are working because we're seeing that on screen, right? We have the vertical bar there just on the left side. That is working. And the DMA request line gets deasserted. I guess that last transfer happens. That's loading that last character into the buffer. And then the interrupt lines that go to the CPU are no longer asserted as well. And then what we have is a whole bunch of time while the CRTC is unloading the buffer into the character generator, and then the next DMA transfer starts. Well, since our capture buffer is so small, I can't see it all. What we can do though is we can change this into stream mode. The problem that's going to happen here is that at 20 megahertz, which is the maximum transfer rate we can do, we can now look and see we have an entire frame, well, we actually have multiple frames of all of the text being transferred into the CRTC. And we can tell because the vertical refresh trigger is telling us exactly where the start of that is. Now the issue is because we're only running at 20 megahertz, if we zoom in, it doesn't always capture the data correctly. And that's really due to the fact that the timing is very close between when the write line goes high and the data bus is set up. And at 20 megahertz, there's just not enough resolution there. And occasionally this will misinterpret what's on the data bus because these two events happen very close to each other. And we can actually see that happening right here. It says press quit TA, it should say to exit, right? But it's miscapturing stuff. And if we look at where it has A, we should be able to see exactly why. Yes, look, see, the transition of write going high happened very close to the data bus just getting, invalid while the SRAM sets up the next value. But that's just because 20 megahertz is just not fast enough for the speed of the transitions that this thing is running at. So if we go back to buffer mode, we can switch this into 50 megahertz mode, which gives us a very short amount of time that we can capture, but it's enough for at least one row of text. And what we can do is change the trigger point to the DAC line, and now we can see correctly what's being transferred from the SRAM into the CRTC. F1, manual dial, and if we look over here, F3, setup, and I just hit capture a few more times, and then check it out. Press quit to exit. Well, that happens to be the very first line in the buffer. And what do we see? We see the letter P perfectly. This first letter P is not currently visible on screen. I mean, you can see the screen right below my face there, and the P is missing, but the P is very clearly there, and it's being transferred perfectly. When the write signal transitions from high to low, the data bus is in perfect order, and it is currently showing P. And we can see that it's a pretty short gap between this going high and the data bus becoming invalid. It's about 0.04 microseconds. But the thing is, when I look at the speed of the other transitions, they're all basically happening in a very similar amount of time. I mean, there's not a lot of resolution because we're only capturing at 50 megahertz, but you can see here, we're at 0.04 between this transition between R and E. Well, and R and E are working perfectly on that first line and never having an issue. The issue only ever exists in that very first character. Now let's do a bit of an experiment. I'm going to fill up the first character of every line with a unique letter or number. And okay, for the first few lines, because if it's kind of annoying how to do this, I put A, B, C, D, E, F on the right side, as you can see right there. But remember, on the left side, I have 1, 2, 3, 4, 5, 6 typed. Oddly enough, we're kind of getting alternates between the very last character, but also a special character now. And that doesn't really make sense because I literally, like where A is here, I had typed 1. And you see if I type 1 twice, but why are we getting the special character there? I don't know. Let's take a look at the logic analyzer and look at exactly what we see for those lines. All right, so I'm going to have to run capture several times so we can actually capture those first few lines. And we're just looking here for that first character to be a 1, 2, 3, 4, 5, or 6. Oh, well, there's that top line, press help, but we, that's what we saw before. Here's a capture of line number 6. So I typed in 2 6s, and I think you should be able to see it down there in the video on the bottom corner. So the right line goes high, and the data bus is correctly set up for the character 6, and that lasts exactly 0.04 microseconds. When we go to the next 6, the duration that it lasts on the bus is exactly the same. It's 4.62 microseconds to 0.466, so 0.04 microseconds again. So everything looks perfect on the data bus. We're not seeing that very last character that's typed in, which, if we scroll over here, what is the last character? It's the letter F. And there it is. F is being transferred correctly in. Remember, you can see the F on the screen down below my face there, and there is F looking perfect on the data bus. There's no sign of that F sticking around on the data bus. The data bus very quickly transitions to a 20, which is a space, for whatever reason. I don't know, the DMA transfer is done, and we can't really see any further than that. But everything is transferring across the bus perfectly. We have a whole lot of spaces, which is exactly what we have. And then at the start, we have the letter 6 twice, which is telling us that's what's stored in the SRAM chip, and that's correct, and it's being set up on the bus correctly. The CRTC should be picking these characters up off the data bus correctly. I mean, remember, the logic analyzer is connected directly onto the pins on the CRTC. I'm not picking up somewhere else, and yet there it is, clear as day. Sometimes, like alternating frames, it's showing the very last character in the row buffer, and other times it's showing, well, I don't know, a graphic character at this point, which doesn't really make sense either. Neither of those should be appearing because in that first column, we should be having 1, 2, 3, 4, 5, 6, and we're not. And unfortunately, based on what I'm seeing here on the logic analyzer, and hopefully I'm analyzing this correctly, there is nothing wrong with this computer at all. Everything is working perfectly. Well, obviously there's something wrong, but there's nothing wrong with the logic or any of the other chips on this machine. Everything is being set up correctly on the bus for DMA transfers. They're happening at the right time. The transitions are correct. The data bus is being set up correctly. The CPU is doing what it should be doing. There really doesn't seem to be anything wrong. The SRAM is obviously working fine. It's storing 6.6 in the buffer, and all those other letters are being stored perfectly, like the P for press. So that leads me, unfortunately, to one conclusion, that the CRTC, the video chip that I put in here, the Siemens one, is also bad. I mean, without a doubt, this one was bad, the Intel one I took off, but this one's either bad, or maybe it has some type of hardware bug where 8-character DMA transfers don't work correctly on it, or perhaps it's running too fast somehow, maybe. And just to reconfirm, this is the clock rate 1.6-ish megahertz going into the CRTC. It comes in on pin 30. The SAB 8275P, which is the version we have here, is rated up to 2 megahertz. So we're not overclocking this chip. It should be working fine at 1.6 megahertz. So I think the data that we've collected with the logic analyzer proves without a doubt that this computer is working fine, and that the issue with that first column missing is the 8275 is just not working, or has a hardware bug, or there's something going on with the Siemens part that is not compatible with the Intel one. So all I can really do is order another CRTC, which really pains me because the Intel ones are a little bit more expensive, and it's not like I have anything else in the entire house that uses one of these. But either way, I'm going to order another one, and let's hope that the second one that comes, which is Intel, by the way, I ordered an Intel one this time, which is probably what I should have done the first time. Will this just fix the issue when I drop the new part in? Or I suppose worst case, it won't fix it, and then I don't even know what I'll do at that point. I have to do something. I have to come up with some kind of solution. I went ahead and I ordered a replacement chip, and this time I ordered an Intel one. Unfortunately, it's taking a while to get here, even though I used a US seller. They didn't ship right away, and it's not going to be here in time, and the saga will continue. So in part 4, we'll try the new chip. Hopefully that fixes the problem. Then I can actually get this thing hooked up to another modem, and we can simulate making a phone call with it. Then I can investigate how the serial port might work, how we can maybe add an RS-232 to this. And I want to add, a viewer reached out and did a full disassembly of the ROMs on the ZT-1 and has come up with all sorts of good stuff about the way it works, including confirming things like the way the DMA transfers work with the MCU emulating the DMA controller, and a lot of the stuff that I just showed with the logic analyzer was confirmed in the code in the ROM. There's some other cool tidbits in the ROM, which I will talk about in part 4, hopefully when this machine is fully operational and working again. Something else that I've gone ahead and ordered besides the replacement chip is I picked up a new 32-channel logic analyzer, one that has a much bigger buffer and a lot faster speeds, and the ability to stream over USB live, which means unlimited capture length, at a much higher rate than that basic unit. So if I need to break out the logic analyzer again to get this thing working, once the new chip is in, well, I'll have more capabilities. But let's hope that's not going to be the case and the new video chip gets this thing working, so we can finally move on to testing some of the other capabilities of this very interesting, fascinating little terminal. So I hope you've been enjoying this video series so far. It's been very fun for me, although a little bit frustrating because I feel like we should have been up and running in this video and been able to demonstrate some of the features, but as was just evidenced by the video you just watched, it didn't go to plan. So anyways, if you liked it, thumbs up. If you didn't, you know what to do. Hit that subscribe button if you haven't already. It makes a big difference to me and the channel to have more subscribers. Thanks to my supporters, their names go up the side of the screen. You make it possible to do this full time. And you know all the other YouTube junk, and I guess that's going to be that. So stay healthy, stay safe, and I'll see you next time. Bye-bye.